Hello dear students, welcome to mathematics class. In this class, let us discuss necessary condition for the function f of z to be analytic. So here, this is the necessary condition for the function f of z to be analytic. There is one more condition, that is sufficient condition for the function to be analytic. So let us study separately. So first, necessary condition for the function to be analytic. So here we know that the definition of the analytic function. Analytic function means the function f of z is said to be analytic if it is defined and differentiable at each point in the domain D or in the region capital R. So here, if f of z equal to u plus iv, where u and v are the functions of x and y. So therefore that can be written as u of x comma y plus I into v of x comma y is analytic in a region R. So now here it is given that f of z is analytic in the region R, then u and v satisfy the CR equations. So we know that what are CR equations? The partial differentiations or the partial derivatives dou u by dou x equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x, provided the partial derivatives dou u by dou x, dou v by dou y, dou u by dou y, dou v by dou x exist. So this is the statement for necessary condition for the function to be analytic. Means if the function is analytic, then the real and imaginary parts of that function of a complex variable will satisfy the CR equations, that is Cauchy-Riemann equations. So let us prove this one, and it is very important regarding the examinations. So here proof, given that what is given here, f of z is equal to u plus iv is analytic. So the definition of the analytic function is the function f of z is defined and differentiable at each point of the domain D or the region R, then it is analytic. So therefore here it is given that f of z is analytic means the function is differentiable at each point in the region R. The function is differentiable means f dash of z, it implies f dash of z exists at each point of the region R. So means at each and every point of the region R, the function is differentiable. It implies f dash of z exists. F dash of z exists means we can write f dash of z is equal to limit as delta z tends to 0 f of z plus delta z minus f of z divided by delta z. So this is by using the definition of differentiation of the function. So f dash of x equal to limit as h tends to 0 f of x plus h minus f of x divided by h. So it is the definition of the derivative of a function. So by using this definition we are writing f dash of z. And now we know that f of z. So f of z is equal to what? U of x comma y plus I into v of x comma y. means u and v both are the functions of x and y. Then f of z plus delta z, f of z plus delta z means there is an increment in the variable z. So, since z equal to x plus iy, then delta z becomes delta x plus I into delta y, means both x and y variables are increased by the quantity delta x. So, therefore, this becomes u of x plus delta x comma y plus delta y plus I into v of x plus delta x comma y plus delta y. So, it is f of z plus delta z, and delta z is equal to delta x plus I into delta y. Now, substituting all these things in the definition f dash of z, then f dash of z is equal to limit as delta z tends to 0. Here it is u of x plus delta x comma y plus delta y plus I into v of x plus delta x comma y plus delta y. This is u of f dash of z plus delta z minus f of z is u of x comma y plus I into v of x comma y whole divided by delta z is there, that is delta x plus I into delta y, and consider this equation as the first equation. So, now we know that the complex variable z equal to x plus iy is either it may be complex, means both the parts x and y are non-zero, but in some cases if y is equal to 0, then it is called as purely real number, and if x is 0, then it is purely imaginary. So, therefore, depending on the real and imaginary parts, we have two cases. Case 1, so let us consider as if delta z is purely real. Purely real means there is no imaginary part. So, therefore, it implies that here we know that delta z equal to delta x plus I delta y. So, purely real means the imaginary part is 0, here the imaginary part is delta y. So, therefore, delta y is equal to 0. If delta y equal to 0, then delta z is equal to only delta x. So, therefore, equation 1 becomes, by applying this condition, the equation 1 becomes f dash of z is equal to limit as delta x tends to 0, because delta z equal to delta x. Then u of x plus delta x comma y, because delta y is 0, plus I into v of x plus delta x comma y minus u of x comma y plus I into v of x comma y whole divided by delta x. Then it is equal to limit as delta x tends to 0. So, now separating the real and imaginary parts in the numerator, then this is u of x plus delta x comma y, and here one more part is there, that is u of x comma y. So it is the real part, means which is independent of I, and here two terms are multiplied by I. One is I into v of x plus delta x comma delta y, and here it is I into v of x comma y. So therefore that is I into v of x plus delta x comma delta y minus v of x comma y divided by delta x. Now let us apply the limit separately for real part and imaginary part. So then that becomes limit as delta x tends to 0, u of x plus delta x comma y minus u of x comma y divided by delta x plus I into limit as delta x tends to 0, v of x plus delta x comma delta y minus v of x comma y divided by delta x. Then it is equal to limit as delta x tends to 0. So by using the here no need to apply the limit again. So by using the definition of f dash of x, so in the definition of f dash of x, what we have, limit as h tends to 0, f of x plus h minus f of x divided by h. But here it is a function of two variables and there is increment only in x, means only x is changing, means we are differentiating only with respect to x, because y is not changed, means we have not differentiated y. So therefore this term can be written as the partial derivative of the function u with respect to x. So therefore that is dou u by dou x plus I into dou v by dou x, and consider this as second equation. So therefore if delta z is purely real, then f dash of z is equal to dou u by dou x plus I into dou v by dou x. Then the second case is if the function is purely imaginary, then what to do, or what will be f dash of z. The second case is if delta z is purely imaginary. So here delta z is equal to delta x plus I delta y. Purely imaginary means there is no real part, so it implies that delta x equal to 0. So therefore delta z is equal to I into delta y. So now delta z becomes I delta y. So therefore equation 1 becomes, so by applying the condition delta x equal to 0, delta z equal to I delta y, then f dash of z equal to limit as delta y tends to 0, u of x comma y plus delta y plus I into v of x comma y plus delta y minus u of x comma y plus I into v of x comma y divided by I into delta y, because delta z equal to I delta y. Then limit as delta y tends to 0. Again here separating the real and imaginary parts in the numerator, we get u into x comma y plus delta y minus u of x comma y plus I into v of x comma y plus delta y minus v of x comma y divided by I into delta y. Now applying the limit separately for real and imaginary parts. So therefore limit as delta y tends to 0, u of x comma y plus delta y minus u of x comma y divided by I delta y plus limit as delta y tends to 0, I into v of x comma y plus delta y minus v of x comma y divided by I delta y. So here I and I get cancelled. It is equal to, here 1 by I is constant taking outside, then limit delta y tends to 0, u of x comma y plus delta y minus u of x comma y divided by delta y plus limit delta y tends to 0, v of x comma y plus delta y minus v of xy divided by delta y. So by using the definition of the f dash of x, here only y is changing, means we are differentiating the function with respect to y. Then it is dou u by dou y plus dou v by dou y. So here 1 by I, so we know that 1 by I is equal to minus I, hence this can be written as dou v by dou y minus I into dou u by dou y, which is equal to f dash of z. It is the third equation. So in the case 1 we have f dash of z, right, but there the expression is dou u by dou x plus I into dou v by dou x, and here dou v by dou y minus I into dou u by dou y. Now let us equate the equations 2 and 3. So from equations 2 and 3 we get, so in equation 2 also it is giving the expression for f dash of z, and third equation is also giving the same expression. So therefore dou u by dou x plus I into dou v by dou x is equal to dou u by dou v by dou y minus I into dou u by dou y. So now here these are the two complex numbers, because it is of the form a plus ib. So whenever two complex numbers are equal, it implies that real and imaginary parts of them are same. So therefore now equating the real and imaginary parts. So equating real and imaginary parts, then it implies dou u by dou x is the real part in the first equation is equal to dou v by dou y, and dou v by dou x is equal to minus dou u by dou y, or this can be written as dou u by dou y equal to minus dou v by dou x. So therefore these are nothing but the CR equations, that is Cauchy-Riemann equations. So therefore which are CR equations, hence if f of z is analytic, if f of z is analytic, it implies that dou u by dou x equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x.